let us study the next injection type, which is group injection. As you can see in this pictorial representation, group injection means a group of stream of particles are injected. Various distributions are available like linear, RR and RR log in order to distribute the sizes of these particles as close as to the real condition. That is, different particles within the stream can have different sizes in practical situations, and we have to represent that size distribution in our simulation. So all these different size distributions are available. All the particle streams are calculated or solved by using particle tracking techniques. Now we will see user inputs that are required in order to set up group injections. The group injection inputs are based on first and last point of the group. That is, we specify the properties or inputs for first point of the group and last point of the group, and all the in-between points or streams are calculated by using size distributions. As you can see, this is the set injection properties panel. Here we specify the first point properties, and in the second column we specify the last point properties. All properties like position, velocity, diameter, temperature, mass flow rate, etc. are to be defined for first and last point, and all the in-between points or particles are calculated by linear variation. So we specify properties for just the first and the last point, and properties for all the points or particle streams in between are calculated by linear variation. Also, for size distribution, Rosin Lambda diameter distribution method is available. Within this method, an assumption is made that exponential relationship exists between the droplet diameter d and the mass fraction of droplets with diameter greater than d. Let us say it is yd. So that mass fraction of droplets is related to the droplet diameter by this particular equation. That is, yd is equal to e raised to minus the ratio of d upon d bar to the power n. D bar is the mean diameter and n is the spread diameter. We have to use Rosin Lambda diameter distribution when we have different sizes of particles within our streams, and we have to give some simpler input in order to represent that diameter distribution. When the particles are injected within the group injections, that distribution is retained, or different size particles are injected by using the Rosin Lambda diameter distribution. We input just the two parameters, that is the mean diameter d bar and the spread diameter d. We don't have to input different diameter for different particles, but what we just input is the mean diameter and the spread diameter, and using these two inputs, Fluent calculates the particle size distribution for different particles using the Rosin Lambda method. Now let us see the steps involved in giving the inputs for the Rosin Lambda method. First, we arrange the droplet size data in terms of Rosin Lambda format. We will see how to do this. Let us say, as an example, we have this type of particle distribution. That is, we know from equipment study or experimental study that we have this type of distribution of particles, or that approximately we have this type of particle distribution within the injections. That is, let's say from 0 to 70 diameter of particles, we have 0.05 mass fraction of that much amount of particles. That is, out of the total number of particles injected, 0.25 fraction are within the diameter range 0 to 70. The particles that are within the diameter range 70 to 100 are 0.1 fraction of the total number of particles injected. And so on. For other diameter range, we have known mass fraction of the total number of particles. So now all this data we have to fit in the Rosin Lambda format. How we do this is shown here. We make two columns of data. First is diameter and second is mass fraction with diameter greater than that particular diameter. That is, first for diameter 70, in front of that we write the mass fraction of particles that are greater than diameter 70. That is, we simply subtract this 0.05 from the total, that is 1, and we get this number as 0.95. So what it means is that the number of particles within the injected stream that are greater than the diameter 70 are 0.95 fraction of the total number of particles. Similarly, the particles that are greater than diameter 100 are 0.85 of the fraction of the total number of particles. And so on, we do this for rest of the particle diameters. As you can see, for 100, what we did is we just subtracted from 1 the addition of these two, which is simple because what we need is just all these. As you can see, 0.85 is nothing but the addition of all these, that is the particles that are greater than diameter 100. That is the mass fraction of particles that is greater than diameter 100. So we obtain this particular graph from our known data. After this, we fit this data into this particular equation, that is Yd, that is the diameter, that is the mass fraction of particles which is greater than diameter d, is equal to e raised to negative of the ratio of d upon d bar to the power n. We fit the data that we obtained, that is this particular data, into this equation. The value of d bar in this equation can be obtained by noting that this is the value of d at which yd is equal to e raised to minus 1. That is, when d is equal to d bar, this becomes minus 1, and so we can obtain the value of d by using yd equal to e raised to minus 1. After we have obtained d bar, n can be found by using this particular equation, which is again derived from the above equation. That is, n is equal to negative of natural logarithm yd, the whole divided by natural logarithm of the ratio d upon d bar. So first we obtain d bar and then we obtain n. And this d bar and n are our inputs for the Rosin Lambda method. Let us see now within the panel what all inputs do we give. We give the total flow rate, which is shown in this panel. This is the total mass flow rate of the streams in the group. We enter it here. Next we give the minimum diameter. This is the smallest diameter to be considered in the size distribution. Next we give the maximum diameter, which is given here, and it is the largest diameter to be considered in the size distribution. Then we give the mean diameter, which is nothing but the d bar value that we calculated with using our steps explained earlier. We give that value here. Next we give the spread parameter, which is the n value that we obtained by using our earlier calculations, and it is given here. This is the exponential parameter. Let us see what user inputs are required for cone injections. First is position. This is how the set injection properties looks like. We select cone injection here in the injection type. We give the position here. These are the coordinates of the origin of the spree cone. If we imagine a cone, then the vertex point of it is this particular position, and we have to give the xyz of that vertex. Next is diameter. We give the diameter here within the point properties section. This is the diameter of the particle. Next is temperature. We input the initial temperature of the stream here. Next is axis. We input the xyz components of the vector defining the cone's axis. A cone will have an axis, and in order to define the axis, we have to give the xyz component of the vector which will define the cone's axis. Next we input the velocity, that is the initial velocity of the particle streams. Then we input the cone angle in degrees. This is the included half angle of the hollow spray cone. If we imagine a spray cone, the half angle of it we will input here in degrees. Next user input for cone injection is radius. This is the non-zero inner radius of the cone. This models the injectors that do not emanate from a single point. Particles will be distributed along the axis with the specified radius. We also input swirl fraction. This is the fraction of the velocity magnitude to go into swirling component. Depending upon the swirl fraction, the amount of velocity that we have specified here will go into swirling component. The direction of the swirl component defined by using the right hand rule. Next input is the mass flow rate. The total mass flow rate for the streams in the spray cone is input here. Let us now discuss the user inputs for plane orifice atomizer injections. For this type, we have to input the position. This is the set injection properties panel. We select the plane orifice atomizer here within the injection type. We select the number of streams. Then we input the position XYZ coordinates of the injected stream. After that, we input the axis. Within the axis, we input the XYZ component of the vector defining the axis of the orifice, which is given here. Next, we input the initial temperature of the stream. After that, we input the mass flow rate, the streams coming out of the atomizer. Then we input the vapor pressure, which is given in pascals. This is the vapor pressure governing the flow through the internal